Hello everyone. So first of all, hope you are doing very well. As you all know that today we will going to cover the theory part 6 of the chemical kinetics chapter. So let's start our today's topic, that is NCERT chapter 3 chemical kinetics theory part 6, in which we will going to cover today NCERT section 3.1 to the NCERT subsection 3.4.1. Let's begin. This is the disclaimer. What are the today's objective? So after attending this lecture, you will be able to discuss the dependence of rate of reactions on the temperature and catalyst. And let's see that what are the topics that we are going to cover today as per the NCERT. In which first of all we will going to cover the section 3.4, which is temperature dependence of rate of reaction. In this, we will cover first of all the Arrhenius equation. Secondly, we will see the activated complex theory, the Boltzmann plot, effect of temperature on the Boltzmann plot, like how the plot given by the Boltzmann will going to affect when you increase or decrease the temperature. What is the Arrhenius plot? Arrhenius equation for two different temperature. Then we will cover the examples from the section 3.4 from 3.9 to 3.10. Then we will shift to our next topic, which is the subsection 3.4.1, effect of catalyst, in which we will study about or talk about catalyst first, and then we will cover the summary part, along with that the key points to remember. Okay, so let's begin. So first, our topic is 3.4, temperature dependence of the rate of a reaction. Most of the chemical reactions are accelerated by increase in the temperature. So if you know the basics of the chemical reaction, any chemical reaction have their particular conditions in which the reaction carrying on, right? What if you increase the temperature of a chemical reaction? What will happen? The atoms or the elements, atoms or molecules which are present in the chemical reaction, they start to heat up and their energy or kinetic energy increases. So they start to move on here and there by the increase of the energy inside them. Right? That's why we are written here that most of chemical reactions are accelerated. So as the movement will increase, the reaction will happen more frequently or more by more speed or by more rate, right? So rate will increase. So most of chemical reactions are accelerated by the increase in the temperature. For example, in the decomposition of N2O5 molecule, time taken for half of original amount of material to decompose is 12 minutes at 50 degrees Celsius, 5 hours at 25 degrees Celsius, and 10 days at 0 degree Celsius. So we are trying to show you that how the increase of the temperature or a decrease of a temperature can affect the rate of a reaction. So when you decompose the molecule N2O5, the oxide of the nitrogen, time taken by this decomposition reaction for half of original amount of material, that means whatever the original concentration of the reactant is present, if you are considering that when how many time is taken by the reaction or by the reactant concentration to convert to the half, okay, so that will depend that it will be going to take 12 minutes if you do the reaction of decomposition at 50 degrees Celsius temperature. It will take 5 hours. The amount is same, that concentration is going to its half in 12 minutes at 50 degrees Celsius, in 5 hours at 25 degrees Celsius, only only if you decrease the temperature by 25, okay, and 10 days at 0 degrees Celsius. So that's how the temperature can affect the rate of a reaction. in a mixture of potassium permanganate KMnO4. So in a mixture of potassium permanganate and oxalic acid H2C2O4, potassium permanganate gets decolorized faster at a higher temperature than that at a lower temperature. Or you can also observe the things in a chemical reaction by the color changing, like the potassium permanganate and the oxalic acid mixture. In this, the potassium permanganate KMnO4 will going to decolorized faster at higher temperature. If you increase the temperature of this reaction, the decolorization happen faster if you compare it with the decolorization process at lower temperature. So for a chemical reaction with rise in temperature by 10 degrees Celsius, the rate constant is nearly doubled. So as I said that temperature will going to affect the rate of reaction, it is also mentioned that for any chemical reaction, if you rise the temperature by only 10 degrees Celsius, the rate constant of that reaction will going to be doubled. So let's suppose we have at T degrees Celsius we are docking. So the rate will be K times the rate constant times the reaction times the reactant concentration. This is the rate law, rate expression which we have studied. Now at T plus 10 degrees Celsius, that means if you increase the temperature with a 10 degrees Celsius increase of temperature, the new rate will become twice of K times the concentration of the reactant. Okay, so rate constant become double when you are increasing the temperature by 10 degree. Then R prime is equals to 2R. You can write it like that because K times R is R, right? So R prime, that new rate is twice of the initial rate at T degree Celsius. Now let's cover our next topic, that is Arrhenius equation. According to the Arrhenius, the rate constant represented by K for a reaction is related to the temperature represented by T by the equation. The equation given is K is equals to rate constant is equals to capital A times e to the power minus EA by RT. So this is the this is a equation called as Arrhenius equation and marked as NCERT equation 3.18. Okay, and according to Arrhenius, the rate constant, that is K, is related to the temperature of the reaction by this given equation, which is named as Arrhenius equation on his name. Here, the capital A you are seeing is a pre-exponential factor, or we also call it as frequency factor. The R is a gas constant, T is the temperature, EA is the activation energy. So T is the absolute temperature, R is a gas constant which has a specific value because it is a constant. This is a plot of potential energy versus the reaction coordinate, that how if you change the potential energy of a reaction, the reaction coordinate is going to change. Let's suppose at this A position we have the energy of the reactants. When you are increasing the potential energy with the increase of reaction coordinate, that means the reaction is undergoing the process to become the products, the reactant is becoming products. There is a state known as activated complex marked as C here in this graph, which forms at which the potential energy of the reaction is the highest. Okay, but after this activated complex point, the potential energy is decreased with the increase of the reaction coordinate and you get the product of the reactant. Okay, and it is denoted by E of P, the energy of product, and marked as B in the graph. Now the energy difference between the energy of reactant and the energy of product is marked as delta H, and the energy difference between the activated complex and the energy of reactant is marked as activation energy. Okay, so according to the Arrhenius, the equation which describes the relationship between the rate constant K and the temperature of a given reaction is defined by Ka times e to the power minus Ea by T, from which we got this plot of potential energy versus the reaction coordinate, where we also define the term activation energy, the energy difference between the energy of the reactants in a reaction to the, or you can say difference between the activated complex energy and the energy of the reactant. This whole quantity is determined as activation energy. Okay. Now let's talk about the activated complex theory. So what is activated complex theory? Let's suppose we have a reaction, hydrogen reacting with the iodine and forming two hydrogen iodide in the gaseous form. According to the Arrhenius, this reaction can take place only when a molecule of hydrogen and a molecule of iodine collide to form an unstable intermediate. So Arrhenius believes on the formation of the activated complex, or you can say intermediate, whose energy is very very high, so it can't be stable. That's why, in the previous graph we have seen that the reactant energy is more than the product energy, because product energy is very less. That means it is going to be stable in the stable form. If the energy is very high, that means it is the intermediate, and E of R is always greater than the E of product, because reactant is going to become the product. That means the reactant having some higher energy than the product, because product is going to be stable, because reactant is converting to the product, right? So this reaction given, and also mention that according to the Arrhenius, this reaction can take place only when a molecule of hydrogen here and a molecule of iodine collide with each other. Collide means the you can say collide means interaction basically. Okay, when hydrogen and the iodine molecules collide with each other, interact with each other, and donate or gain the electrons or exchange the electrons between each other, then a unstable intermediate will form first of all before the product formation. Okay, let's see this in the figure 3.6, which is given as this. This is showing the formation of hydrogen iodide through the intermediate. So two hydrogen atoms combining to form one hydrogen molecule, two iodine atoms combine to form iodine molecule, and the hydrogen molecule and iodine molecules are reacting together, combining together, colliding together, or more specific, to form a intermediate which is kind of unstable, because the intermolecular force will going to act upon, and this dotted line is showing that bond is starting to form. Okay, so H and I bond is starting to form, and HHII bond is starting to break. Okay, then this intermediate will convert to these two products, that is 2 of HI. Okay, it exists for a very short time and then breaks up to form two molecules of hydrogen iodide. As you can see, that intermediate is unstable. We have mentioned that intermediate is an unstable compound. That means anything, if in the chemistry, if anything is unstable, it wants to be stable, right? So it try every way to become stable. So unstable intermediate exists for very short time, and then it will break up to form the two molecules of hydrogen iodide in this reaction, in this case. Okay, before moving on further, I want to mention that if you are having any doubt in between of the lecture as per the content, you can ask that in the chat box, please. Coming back to our point, this intermediate is known as activated complex. Okay, so the intermediate which we are talking about for this particular reaction, the intermediate which is forming, which is unstable, very short time existence it has, and it breakups into two molecules of hydrogen iodide. This intermediate is known as activated complex. Remember, in the graph we have mentioned the activated complex energy very very high from the energy of reactant and from the energy of product comparatively, right? So that is the reason that, because its energy is very very high, it is very very unstable, and it wants to be stabilized by the formation of the product. The energy required to form this activated complex is known as activation energy. Now that remember that difference between the activated complex energy and the reactant energy, that difference we have marked as activation energy. So the energy which is required to form the activated complex C is known as activation energy, represents by E subscript A. Okay, now let's talk about our next major topic, that is Boltzmann plot. Until now we have seen the Arrhenius equation and Arrhenius plot. All the molecules in the reacting species do not have same kinetic energy. Now, what we are saying that any in any chemical reaction we have either one or more than one reactant. Okay, basically generally it is going to be more than one, so that the two molecules, we are considering general case, so that the two molecules will react or collide with each other and form a product, right? Product can also form more than one. So all the molecules which are present in the reacting species, that sorry, so the reacting species means the reactants which are reacting together, the molecules which are reacting together, it is not necessary that they have the same kinetic energy. Okay, uh, every reactant in the reaction not necessarily have same kinetic energy. Ludwig Boltzmann and James Clerk Maxwell used statistics to predict the behavior of large number of molecules. Now these two scientists used the statistics at that time to predict the behavior of large number of molecules, that whether their kinetic energy will be larger or the smaller one between the two reacting species. Okay, so according to them, they said that the distribution of kinetic energy may be described by plotting the fraction of molecules with a given kinetic energy versus kinetic energy. Okay, so according to them, if you want to check the kinetic energy for the reacting species, right? So how the distribution of kinetic energy happened, why it is not same in all the reacting species, that distribution of kinetic energy you can describe by plotting fraction of molecules with given kinetic energy, whose kinetic energy is known, the fraction of molecules versus kinetic energy. Okay, let's see this plot in the figure 3.8, which is this one. The figure 3.8 showing the distribution curve and showing the energies among the gaseous molecules. So this curve is a first of all increase and then decreasing curve. At the y-axis we have fraction of molecules, and the and the x-axis represents the kinetic energy. With the increase of the kinetic energy, the fraction of molecule is increasing initially, but at after a point reached, maximum point reached, the kinetic energy increases but fraction of molecules decreases. Okay, so this point at which the fraction of molecules is highest at a particular kinetic energy value, this point represents the most probable kinetic energy that a molecule or a fraction of molecule can have. Okay, so that is the graph which is representing that as you are increasing the fraction of molecules, some fraction of molecule will get the increasing value of kinetic energy, another will get the decreasing value of kinetic energy, and the particular value of kinetic energy at which the fraction of molecule point maximum point is given, that this represents the most probable kinetic energy that a reacting species can have in a particular chemical reaction. Okay, fraction of molecules Ne by Nt. Okay, so let's see the temperature dependence of the rate of a reaction. So this was the Boltzmann plot we have seen, right, between the fraction of the molecules and the kinetic energy. Okay, so figure 3.8 distribution curve, which is showing the energies among the gaseous molecules. Ne is the number of molecules with the energy E, and Nt is the total number of molecules. Okay, so the fraction of molecules was Ne by Nt, right? Where Ne is the number of molecules who is having energy E, and Nt is the total number of molecules present. Peak of the curve corresponds to most probable kinetic energy, that is the kinetic energy of maximum fraction of molecules. So as I said, that this peak of the curve representing by this point, and this is representing the most probable kinetic energy, that means the kinetic energy of maximum fraction of molecules, that means maximum amount of fraction of molecules that are having this kinetic energy, that this point most probable kinetic energy is corresponding to that. Okay, this is the peak of curve. There are decreasing number of molecules with the energies higher or lower than this value. Okay, and also this most probable kinetic energy value, higher, either higher or lower than this value, there are numbers of molecules that are decreasing. Right here also, if you see the, like, if you move from this point to the left hand side, then also the graph is decreasing. Right hand side, the graph is decreasing. Okay, so if you move, or if you see the molecules with the energies higher or either lower than this most probable kinetic energy, that number of molecule is decreasing, right? Now let's talk about the effect of temperature on the Boltzmann plot. Initially we have talked about the Arrhenius plot, where we have seen the effect of temperature on the rate constant. Here on the Boltzmann plot, how the temperature will going to affect. So when the temperature is raised, when the temperature is increased, maximum of curve moves to higher energy value. Okay, so as the temperature increase, if you rise, as I said, that if you rise the temperature for a particular chemical reaction, the energy present or the energy of the reactant species is going to get increased, due to which they get more mobile, they start to move here and there more frequently. So the maximum of curve, the most probable kinetic energy we just have seen, that maximum of curve moves to the higher energy value, which is shown in the figure 3.9. We will just see that. And the curves broaden out also with the increase in with the increase of the temperature, the curve will going to broad up, that is spreads to the right, such that there is a greater proportion of molecule with much higher energies. So this curve will going to broaden out, that means it will going to spread to the right direction, such that there is a great proportion of molecules, because y is representing the fraction of molecules, right? So if the curve is going to broaden out, that means the area under the curve, which is showing the fraction of the molecules having the particular value of the kinetic energy, that fraction of molecule is increasing with the broaden out of the curve, right? So when the curve will broad out, it will spreads to the right direction, such that the greater proportion of molecule will cover in this with much higher energies. This is the figure 3.9, which is showing the distribution curve, showing the temperature dependence of rate of reaction. So same curve as Boltzmann plot. X-axis denoting the kinetic energy, y-axis vertically denoting the fraction of molecules. There are two graphs. So the first graph is represented at the time, okay, as the temperature T, and you can see that when you increase the temperature by 10 degree, T plus 10, the graph will going to broad out and going to spread out to the right. So you can see that the peak point is also shifted. Now we have some area, the darker one and the lighter shade one. The darker shade area is showing the fraction of molecules which are reacting at the T temperature, but this lighter shade area is showing the fraction of additional molecules which react at the increasing temperature, which is T plus 10. Okay, the energy of activation is showing this line is shown by this line, the vertical line. Okay, energy of activation. So this is the graph showing that how the effect of temperature, that how the temperature is going to affect on the Boltzmann plot. So how If the temperature will raise, the Boltzmann plot will going to broaden out and the curve will spread to the right such that there is greater proportion of molecules with the higher energies. Area under the curve must be constant since the total probability must be 1 at all times, right? So the total probability means the total number of fractions of molecules that going to cover inside this curve that represents the area under the curve, that must be constant, because the total probability, if you have studied, total probability will always be equals to 1, right? Now, if you have seen, we have just seen this figure 3.9 showing the effect of temperature on the Boltzmann plot. Increasing the temperature of the substance increases the fraction of molecules which collide with the energies greater than the activation energy EA. What we are saying, if you increase the temperature of substance in a chemical reaction, it will increase the fraction of molecules, okay, which will going to collide with the energy greater than EA, because with the increase of the temperature, their energy is also increased. So the fraction of molecules increases because they will going to collide with higher energies or higher energy molecules which have energy greater than EA if you increase the temperature. In the curve at T plus 10 temperature in the figure 3.9, area showing the fraction of molecules having energy equal to or greater than activation energy gets doubled, leading to doubling the rate of a reaction. So what we are saying, that in the curve T plus 10, which is this lower curve, okay, representing as T plus 10, this one is T and this one is at T plus 10. So in this curve at T plus 10 temperature, with the area which is showing the fraction of molecules having the energy equal to or greater than activation energy will going to get doubled, leading to doubling the rate of a reaction. So this area is increased, right? From the previous graph, this T plus 10 graph, the area of the graph is increased. And if it is increased and temperature is also increased, right? T plus 10. So area which is showing the fraction of molecules having some amount of or some number of energy which is equal to or maybe greater than activation energy gets doubled. So area doubled, temperature also increased by 10 degree, which leading to the doubling of the rate of the reaction. Okay. And always, like I said, that temperature increase will going to affect positively on the chemical reaction because it will going to double the rate of reaction or increase the speed of the reaction. Now let's see the Arrhenius plot. So the Arrhenius equation given by the Arrhenius was K is equals to A e to the power minus EA by RT. R is a gas constant, T is a temperature, absolute temperature, EA is activation energy, A is Arrhenius constant, and K is rate constant. This is representing the NCERT equation marked as 3.18. Now, how you plot the Arrhenius plot? You use this Arrhenius equation given by Arrhenius, and then after using this, you will going to plot the Arrhenius plot. So what we are doing, the first step is taking natural logarithm of both sides. In this equation, we take the log at both sides. So the log of k will become ln k is equals to log of a, so ln a minus log of, okay, now here you have to understand the property of log. So when you take the log of right hand side, it will become the log of a times e to the power minus a by rt, right? So you take first of all the log of a, then the log of e. You apply a particular formula. There is a particular formula for this property, that when you are applying the log property between the two things which are in the product, Okay, like here a and e to the power minus ea by rt. Then you apply that formula, which is called as log of uv. Okay, then you get this result as ln a minus ea by rt. You get this ea by rt in the equation because it is already present in the e to the power. Okay, ln e is going to be 1, and whatever is present in the power of the ln, that is going to become in the product side. That's why we are writing here minus ea by rt in the equation, not in the power. Okay, so ln k is equals to ln a minus ea by rt. This is the ncrt equation marked as 3.19. If you plot the ln k versus the 1 by t graph, it will give you a straight line according to the equation 3.19 we just have seen as shown in the figure 3.10. So what is figure 3.10? It is this one, which is a plot between the ln k and 1 by t. So ln k is representing in the vertical axis, which is y-axis ln k, and on the x-axis we have 1 by t. The line we are getting is a straight line with a negative slope. Slope is minus ea by r because it's a decreasing line. And the intercept, that at x equals to 0 or at 1 by t is equals to 0, the intercept you are getting on y-axis is ln a. Okay, so plot of ln k versus 1 by t as shown in the figure 3.10 is a straight line according to the equation 3.19. Now let's see that Arrhenius equation for two different temperature. What is the equation of Arrhenius? So basically equation of Arrhenius was a is equals to k is equals to a e to the power minus ea by rt, right? But t there is only representing one temperature. What if we are talking about the Arrhenius equation at two different temperature? So at temperature T1, let's say the equation 3.1 is 19. 3.19 is ln K1 is equals to minus of EA by RT1 plus ln A. At temperature T1, we have ln K as ln K1, EA by RT as EA by RT1. Rest is same, right? This equation is representing the NCRT equation 3.20. Now, similarly, at temperature T2, the equation 3.19 is ln K2 is equals to minus of EA by R T2 plus ln A. Okay, so K2, T2, so that's why at temperature T2, the equation 3.19 becomes this equation, which is marked as NCRT equation 3.21. Now, since A is a constant for a given reaction, because it is a Arrhenius constant, it will be going to be constant. Its value is already going to be given to you. So, since A is a constant for a given reaction, the K1 and the K2 are values of rate constant and temperatures T1 and T2 respectively. Okay, so here in this two equation 3.20 and 3.21, the K1 and the K2 is representing the value of the rate constant. T1 and T2 is representing the value of the temperature, the two different temperature at which we are talking about the Arrhenius equation. Okay. If anyone has any doubt, they can ask in between in the chat box. Continuing on this topic, let's subtract the equation 3.20, which is this one. ln k1 equals to minus of EA by R T1 plus ln A from the equation 3.21, which is ln of K2 is equals to minus EA by R T2 plus ln A. Okay, when you subtract these two equations, you will going to obtain ln K2 minus ln K1. So this minus this 3.21 minus 3.20. This is going to be equals to EA by RT1 minus EA by RT2. Okay, rest amount will going to cancel out. They will going to cancel out because they are equal. Only sign will change. So that's why this is the equation we get from the subtraction of equation 3.21 to equation 3.20. ln K2 minus ln K1 is equals to EA by RT1 minus EA by R T2. Now, you can write the ln A minus ln B as ln A by B. So, ln of K2 by K1 is equals to, you take the EA by R common from these two terms. So, EA by R, remaining thing will be 1 by T1 minus 1 by T2. Okay, so what we did, we apply a log application or log use or log formula, that log A minus log B will be log A by B. So ln K2 by K1 is equals to, the EA by R is a constant in both the terms of this reaction. So EA by R, when you take it as constant, the remaining thing will be go in the bracket, which is 1 by T1 minus 1 by T2. So you can take this equation like that in the ln form, or if you want to convert it in the log form by multiplication of 2.303 into the value, you convert the ln from ln to the log. So log of K2 by K1 is equals to EA upon R is going to be R, which is a constant value. We have multiplied 2.303 to convert the ln to log, and when you do the multiplication, this product thing which is present at the product side in the left hand side will go at denominator in the right hand side, and the rest thing are same. Log K2 by K1 equals to EA upon 2.303 R times 1 by T1 minus 1 by T2. This equation is representing NCERT equation 3.22. Now log of K2 by K1 is equals to EA upon 2.303 R multiply by T2 minus T1 upon T1 T2. So we just take the LCM inside the bracket. Okay, now let's see an example which is marked as 3.9 in our NCERT textbook in the chapter Chemical Kinetics. The example is saying that rate constant of a reaction at 500 Kelvin and 700 Kelvin are 0.02 second inverse and 0.07 second inverse respectively. You have to calculate the values of EA and A. Okay, so you have to calculate the value of activation energy and the Arrhenius constant. If you have given the rate constant of a reaction at two different temperatures, then. So you got some time until whatever we have studied till now, try to remember that and try to apply one of the formulas from that to this question. Then we will see what is the correct answer. Okay, let's see. So for this particular question, so according to the Arrhenius equation for two different temperatures, the log of K2 by K1 is equals to EA upon 2.303 R T2 minus T1 upon T1 T2, right? This is the equation of the Arrhenius at two different temperatures T1 and T2. So we know that the K2 by K1, that is rate constant, different values at different temperature are already given. The temperature are already given. The EA is what you have to find out from this equation. So log of 0.07 by 0.02 is equals to EA upon 2.303 multiplied by R is 8.314 joule Kelvin inverse mole inverse, multiply by T2, T2 is 700, T1 is 500. So 700 minus 500 upon 700 into 500, T1, T2, right? Now in this whole equation, only the variable or unknown is EA, that is activation energy. So you have to calculate for this. So 0.544 is equals to EA multiplied by 5.714 multiplied by 10 to the power minus 4 divided by 19.5. When you simplify it more, the EA will be 0.544 multiplied by 19.15 divided by 5.714 multiplied by 10 to the power minus 4. Now EA is coming out after solving this fraction as 18230, that is 18,230.8 joule. Now what else we have to also identify? The A, the activation, the Arrhenius constant. So since the K, according to the Arrhenius equation, the K, that is rate constant, is going to be equals to Arrhenius constant times e to the power minus EA by RT, which is NCRT equation 3.18. The K we have, which is 0.02, at the T1 500. So it is equals to A e to the power minus 18,230.8 divided by 8.314 multiplied by 500. From here, the A is coming out as 0.02 divided by 0.012. So the A will be, after solving this fraction, 1.61. So this will be going to the correct answer for the value of A, that is the Arrhenius constant. Okay. Let's see the another example, which is marked as example 3.10. It is saying that first order rate constant for decomposition of ethyl iodide by the reaction C2H5I undergoing the decomposition reaction and becoming C2H4 plus HI at 600 Kelvin is 1.6 times 10 to the power minus 5 second inverse. So this is the rate constant value for a first order reaction of ethyl iodide. Now its energy of activation is 209 kilojoule per mole. We have to calculate the rate constant of reaction at 700 Kelvin. So you have given some time. Try to solve this and then we will see that how you can solve this and what will be the correct answer. Okay, let's see. So for this given question, we know that according to Arrhenius equation for two different temperature, you can write it as log K2 minus K log K1. Basically, it is log K2 by K1. You can write it as log K2 minus log K1 is equals to EA upon 2.303 R multiply by 1 upon T1 minus 1 upon T2. Now, you take this log K1 and from the negative to the positive in the right hand side. So, log K2 will be equals to log K1 plus EA upon 2.303 R times 1 by T1 minus 1 by T2. Now, log of K1 is already given, which is 1.60 times 10 to the power minus 5, rate constant value, right? So, log of 1.6 times 10 to the power minus 5 plus EA activation energy is already given 209 kilojoule. You have to convert it into the joules. So, kilojoules to joules will be multiplied by 1000. So, 209 multiplied by 1000, that is 2,09,000 basically joule per mole divided by 2.303 and multiply by R value, which is 8.314 joule per mole per Kelvin. T1 and T2, they are 1 by 600 minus 1 by 700 because at T1 we have given the rate constant value. At T2, that is 700, we have to find out the rate constant value, right? So the K2 you have to find out. Other than that, we have to solve this whole equation. So log of K2 will be equals to log of this, which is minus of 4.796 plus this whole fraction, which is coming out as 2.599, and when you do the subtraction it will be minus 2.197 So log K2 is minus 2.197. So K2 will be 6.36 multiplied by 10 to the power minus 3 second inverse. Okay. So how you got log K2 equals to this? So log base 10, base is 10 basically in the log. So log base 10 K2 is something. Let's say log base 10 K2 is x. So K2 will be 10 to the power minus x. Okay. Now take x as minus 2.197. So log K2 is minus 2.197. So K2 will be 10 to the power minus 2.197. And when you solve this, that how much the 10 to the power minus 2.17 will be, it will be 6.36 times 10 to the power minus 3 in the second inverse units. So this is the rate constant value at the 700 Kelvin temperature for this given reaction of decomposition of ethyl iodide. Hence, this will be our answer. Okay. Okay, now let's talk about the next topic, that is 3.4.1 effect of catalyst, in which let's talk about a little with catalyst. So catalyst only lowers the activation energy. As you all know, catalyst is a element or a molecule you can use to increase the rate of a reaction, to speed up the reaction, and it is not going to affect the reaction, or you can say that it is not going to participate in the reaction, and you can add the catalyst inside the reaction, and you can get back the as it is amount of the catalyst after the completion of the reaction. So catalyst only lowers the activation energy. Activation energy represents by EA. Catalyst does not alter the Gibbs energy, that is delta G of a reaction. It catalyzes the spontaneous reactions but does not catalyze non-spontaneous reactions. So spontaneous reactions are those reactions which can happen spontaneously and whose delta G value, that is Gibbs energy value, is lesser than 0. But the non-spontaneous reactions whose delta G value is greater than 0, which can't happen spontaneously. So catalyst is only catalyze the spontaneous reaction, does not catalyze non-spontaneous reactions. It increase the rate of both backward and the forward reaction. If you use the catalyst in an equilibrium reaction, it is going to increase the rate of the backward and the forward, both type of reactions. Backward means the product is converting to the reactant again. Forward means the reactant is converting to the product. For example, MnO2 catalyze following reaction so as to increase its rate considerably. So 2KClO3, when you add a catalyst of MnO2 in this reaction, it is going to increase its rate, the reaction rate, and form the products 2KCl plus 3 oxygen molecules. The word catalyst should not be used when the added substance reduces the rate of a reaction. Okay, so we can't use the word catalyst for a adding substance which we have added in the reaction if that is going to reduce the rate of reaction. If the rate of reaction is decreasing, reducing, that means the substance we are adding into the reaction, we can't call it as catalyst. Substance is then called inhibitor. Then what you can call that substance which are reducing the rate for the reaction, you can call it as inhibitor. Now the effect of catalyst. So catalyst does not provide energy for the reaction. It is not as temperature, like temperature increase provide the energy in the molecules or in the atoms, which will going to affect the molecules, and they will go here and there, or they will become more mobile to increase the rate. But the catalyst will not going to provide any energy for the reaction. It provides an alternative pathway for the reaction to occur by reducing the activation energy between reactants and products. So there is a different or alternative pathway for a working of a catalyst, that it will provide to the reaction a alternate pathway by reducing the activation energy. Basically, it will going to reduce the activation energy between the reactant and the products to become the catalyst or to perform as a catalyst to increase the rate of a reaction. It will not going to provide any energy, or it will not going to affect any energy for the reaction. New pathway has lower activation energy, and hence the reactions occur at higher rate. Catalyst has no effect on enthalpy of the reaction and no effect on the delta G, that is free energy of the reaction. Okay, so catalyst also not affect the enthalpy of the reaction, like different type of enthalpy, enthalpy of atomization, enthalpy of dissociation, or enthalpy of there are many type of enthalpy. Enthalpy means energy basically. Okay, so catalyst has no effect on the enthalpy of reaction, and there is also no effect of catalyst on the delta G of the reaction, free energy of reaction, as shown in the figure 3.11, which is this. The figure 3.11 showing the effect of catalyst on the activation energy. So potential energy versus the reaction coordinate graph, and as you can see, this graph is a curve where the reactant energy is different, product energy is different, and we have already getting a highest energy or potential energy in this reaction, or you can say product formation. Okay, this dotted graph is the second graph, which is showing the reaction path with the catalyst, in which the activation energy gets decreased. Okay, and the reaction rate will increased. So this is the the lined graph is a reaction path without catalyst. The dotted graph is a reaction path with catalyst. And same as I said, that highest potential energy, which is marked for the lined graph, and the reactant energy, and the difference between them is showing the energy of activation without catalyst. Meanwhile, the highest energy in the dotted graph and the energy of the reactant, and the energy difference between them is the energy of activation with the catalyst. Okay, so this is kind of the plot which is showing the effect of catalyst, that if you add a catalyst inside a reaction, how it will going to affect the rate by reducing the activation energy of the reaction. Okay, so thank you so much. That's all for today's chemistry session. Kindly wait for some more time. Your next faculty for the physics will join you soon. Thank you so much.